Good morning. We will today start a new topic, that is the torsion of non-circular bars. So in the previous semester you have studied the torsion of circular bars. So that is the regular torsion formula. Anybody recollect what is the torsion formula? Torsion equation. So T is related, the torque is related to the stress, shear stress. So you have P by J equal to G theta upon L equal to That's it. So this particular equation is valid only for circular cross section. In general, if the cross section is not circular, then what happens is what we are going to see now. So this formula is a special case of the general theory that we are going to cover in this class. So first, where do you need non-circular cross section? So anybody can think of some applications where non-circular cross section is used for torque transmission? Drill bit, okay. So drill bit has got very odd shape. It's not circular, near circular but not circular. Okay, that's right. So drill bit is a good example. What else? Any other cross section that has non-circular cross section? Okay, I'll show you some pictures. You can add to that. So you must have used sometimes the Allen key for tightening the nuts or screws. Then wherever you are using your key, whenever you are turning the key cross section is a rectangular and you are applying torque to it. Very small torque, but you will require that. If you look at the assembly of the handle, inside the handle, whatever rod passes through, it has got a square cross section, square or rectangular cross section, so that it latches with the inside mechanism easily. And robotic arms, so they also could be circular cross section, but there could be any other cross section depending on what weight optimization purpose you require. You may not require circular, you may require some other cross section. So that is 3 examples I given. Drill bit, he has already given 4th example. Anything comes to your mind which utilizes non-circular cross section for the transmission of torque? I have covered all non-circular cross sections. There are plenty of examples. One would be the tip of the screwdriver, which is similar to the Allen key but different than the Allen key. So the tip of the screwdriver is a rectangular, which is subjected to torsion. Okay, so when you are designing such component, the regular circular cross section theory sometimes is used as an approximation. So if you have a rectangular cross section, what approximation one does is this J value, which is the polar area moment of inertia. You consider polar area moment of inertia of this rectangular cross section, and R value you take from its centroid, what is the maximum, the farthest location that you consider as the R location, and one uses this formula. But that is incorrect in the sense it is highly approximate. But as a crude way of doing the calculations, one would use the circular torsion formula to handle the non-circular cross sections. But more accurate way of doing that is what we are going to see today. Before we go into why the non-circular cross sections require a different treatment, we'll understand through a small video what is the main difference between twisting a circular cross section and twisting a non-circular cross section. So we'll see one small video which will illustrate this thing.
In this video, we are quickly going to look at why the formulas we've derived thus far only apply to circular shafts. If you recall, a circular shaft subjected to torsion will deform in a way such that planes perpendicular to the axis of the shaft remain straight, do not warp or distort, and do not extend relative to each other. Furthermore, lines parallel to the axis of the shaft also remain straight, but rotate through an angle. From these observations, we deduced that there is a state of pure shear in a shaft subjected to torsion, and this shear stress varies linearly with radial position. If we take a closer look at this stress state superimposed on the cross-section of a circular shaft, it will appear as shown here at one angular position within the shaft cross-section. Now, in reality, this stress distribution exists at all angular positions. And in a way, you can visualize this as a flow of that stress around the axis of the shaft. Applying this fluid flow analogy to a non-circular cross-section, such as the rectangular one shown here, it becomes immediately apparent that the shear stress distribution will be far more complex. As we sweep through various angular positions, the fluid flow, or the stress flow, around that cross-section will warp and change to maintain the same resultant flow around that cross-section. Thus, for non-circular cross-sections with this variable geometry, we'll have a very complex stress state as illustrated here on the rectangular cross-section. We can visualize the impact of this complicated shear stress distribution by observing the deformation of this flexible rectangular shaft. Two lines perpendicular to the axis of the shaft have been drawn on the surface of the shaft. If a cyclic torque is applied to that shaft, you see that the lines actually deform. They warp from their initially straight position to a S shape as the torque is applied and removed. This is an indication that the assumptions that we made for circular shafts, that those planes remain plane, are no longer valid. It is possible to derive formulas for the shear stress and angle of twist for non-circular shafts, and many engineering handbooks have tabulated results, such as the one shown here, for specific geometries. However, for the same cross...
So after this, whatever he is explaining, we are going to see in the classroom. So what essentially this video tells you, okay, can somebody tell what are the two differences, or what are the differences we discussed in the video between the circular cross-section twisting and non-circular cross-section twisting? So what is the difference you observed?
The planes will remain same.
So what do you mean?
Those two lines don't remain on the same.
They don't remain in the same plane, whereas in the circular cross-section, they remain in the same plane. So if you twist this particular plane, which is circular, if you draw a line that is a circular cross-section, it will not change its position. The circle will twist in the same plane, whereas if it is a rectangular, then the same straight line, it will take a S shape. So that is called as a warping, and that forms an important part of the calculations that we are going to do afterwards. And there is also concept of shear flow, which is new to you, that we'll also touch upon towards the end. So you can visualize the stress distribution inside the cross section as that of some kind of fluid which is flowing in the direction of torque, and as the fluid moves, the velocity can be related or analogously considered as that of the shear stress. So you will find that the distribution of shear stress in circular cross section is a linear, whereas in case of non-circular, depending on what is the cross section, it will be non-linear. So these are the two differences which we will see in the subsequent discussion. So let's proceed. So let's consider twisting of a cross section. So this particular point, let me emphasize once again that in the main difference is that in the circular cross section, the lines or the cross sections, even after twisting, they remain flat, whereas in case of non-circular, they will take a warping, or there will have be a movement along the axis of the shaft or axis of the body which is being twisted. So that plays an important part in the subsequent discussion that we are going to discuss. So let's quickly understand how this particular phenomena can be captured. So what we are interested in non-circular shaft design or in the analysis is that when such a non-circular shaft is twisted, subjected to some external torque, we want to calculate what is the maximum shear stress that is getting induced. For us to check how to design it, we will limit that maximum stress within the allowable material stress. And second thing, how much it is deforming. For some applications, such as in machine tools, we want to have the spindle or some tool holder to be very rigid. So we want to control the deformation. So we would also like to know what is the deformation being produced when we are twisting a non-circular shaft. There are different approaches to develop the final equation which we are going to use. The one approach is called as a displacement based approach. So in this approach, first we establish when a non-circular shaft is rotated, how each point in the cross section gets displaced. So we'll first formulate what is Ux, Uy and Uz for any point in the cross section, and from that we will get the stress equation. So that is the approach is called as displacement based approach or Saint-Pinant approach. So that approach is being followed here. Some definitions. So the coordinate system, so this is the shaft. The axis of the shaft is the z axis. So this is the non-circular shaft. The axis of this pen is the z axis, and xy axis is the one where the cross section lies. So xy axis contains the cross section of this particular shaft. The theta, which relates to the deformation or flexibility of this particular shaft, is defined here is angle of twist per unit length. So consider this particular shaft is fixed at the left side end, and you want to know what is the angle of rotation at a distance z along the axis of this particular shaft. You have to multiply z, which is the length of this shaft, to this angle theta. So theta is angle of twist per unit length. So if you multiply by the length of the shaft, you will know at that location how much is going to be angle of twist. So in torsion, always there is one end is fixed, or you can consider as a relative fixed end, and with respect to that, all the deformations would be calculated. So theta gives us the angle of twist, which is of course unknown, and we are trying to find out this particular component. As I said, this is a displacement approach. So we'll first establish what are the equations for Ux, Uy and Uz for any point in the cross section of this particular shaft. So for that purpose, we will consider a diagram as follows. So what we are considering here, so we have got x-axis, we have got y-axis, and we have got the cross section of this particular body that we discussed here. So we are considering some point P in this particular body, and we want to establish what is the x direction displacement of this point, y direction displacement, and z direction displacement of this particular point. Now this particular figure is zoomed up here, so this is the point P that we are discussing. So this is the point, the original position of the point. Now because we are applying torque to this particular shaft, this point is going to twist, so it is going to move, and that movement is given so that the original point P becomes P dash. So this P dash point is as defined in this particular diagram. So we know the net displacement of this particular point with respect to whatever is the angle of twist of this particular point. So angle of twist, as I said earlier, the theta is angle of twist per unit angle. So this is per unit length. So this is angle of twist per unit length. And we are considering this particular point to be, or this particular cross section to be at the distance z from the origin. So at this cross section, the angle of twist will be theta multiplied by the length from the fixed edge. So theta multiplied by z would be the angle of twist which will occur at this particular point. So original point P will get twisted through an angle which is equal to theta times whatever is the length of that cross section with respect to fixed edge. So that is what has been shown here. So angle of twist here would be theta multiplied by z. So this is the angle of twist this particular point is undergoing. Okay, now this particular point coordinates are x and y. In polar coordinate, we can define this particular point as located at a distance r, so this is r, and at an angle which is beta with respect to the x-axis. The ultimate why we are doing this is to calculate the displacement of this point, that is what is the ux and ui when it has undergone this particular twist. So for that purpose, concentrate on this particular triangle. For very small displacement, you can consider this particular arc. So actually this particular P to P dash is a circular arc, but we are considering very small displacement. We can assume it to be a very short line. What will be the length of this line? It can be calculated from radius multiplied by angle of twist. So angle of twist is theta z and radius is r. So what would be the length of this P to P dash? R multiplied by theta into z. So that is what has been done here. So r into theta z is the length of the hypotenuse of this particular right angle triangle. Now if you note here, the base of this right angle triangle is nothing but the displacement. The point P has moved in the x direction by distance ux, and the point has also moved in the y direction by a distance which is ui. So we can calculate, or we can write down ux and ui in terms of the hypotenuse using the properties, the trigonometry of this particular triangle. If you look at this particular triangle, it is similar to the triangle which is shown here. So this particular angle is also equal to beta. If you look, these two triangles are similar, and this particular angle is this equal to the angle of this particular right angle triangle. So this angle is beta. So we can now write ux in terms of the hypotenuse and this particular angle. So I want to calculate ux. So can you tell by trigonometry ux will be how much? It will be r theta z multiplied by sine of beta. So that is how it will become. So r theta z is hypotenuse multiplied by sine of beta is the value of ux. So everybody is clear till here? Okay, now we'll simplify this. We'll write this equation as theta multiplied by r sine beta multiplied by z. So I just rearrange the terms. I've written theta multiplied by r sine beta multiplied by z. Now look at the triangle which is shown here. Look at this triangle. Where this dimension is r and this angle is beta. So can you tell what is the value of r sine beta? So this distance is r and this angle is beta. So r sine beta is nothing but this distance. Correct? And what is this distance in terms of coordinates of this point? It is the y coordinate of this particular point. So this particular ux can be written as theta multiplied by y multiplied by z. So we got the first component that we wanted. So ux is given as theta into y into z. One more observation you will note here. So this is a magnitude wise we are doing. If you note the displacement of point P for positive theta or theta as shown here, the point P is moving in the negative x direction. So it is magnitude wise it is ux what we have calculated, but sign wise it is in the negative x direction. So ux will be equal to minus theta into yz. So this is the magnitude. But we have to assign sign with respect to whether it is moving in positive x-axis or in the negative x-axis. So this, considering this theta direction as positive theta, so if the theta is positive, so ux would be negative. So that is what this particular equation means. Similarly, we can calculate ui by using the same technique, and you will get ui equal to plus theta x multiplied by z. So that is the second equation you will get. By the same logic you will get it. You will get it r theta z into cos beta, and r into cos beta is nothing but the x-axis or the x coordinate of the point. So ux and ui are defined as given here. Now we know that a non-circular shaft, by that video, whenever it is subjected to a twist, it gets warped. So what you mean by warping is that some points will move forward, some points will move backward. So we'll have the cross section which is somewhere it has moved along the axis forward direction, somewhere it has moved in the backward direction. So that is what that S shape would mean. So that means there will be some displacement in the z direction as well. That z direction displacement is covered by something called as a warping function. So this is another unknown. So we will see later, for every cross section this warping function will be different. For circular cross section, warping function will be something. For rectangular or square cross section it will be another. For triangular it will be third. Our job is to find out a warping function corresponding to every cross section in general. At present we don't know what is the nature of this warping, but we know that there will be some displacement in z direction, and that is given by this function psi. So this is the Greek letter which is pronounced as psi. So this particular function we will be using for defining the z displacement. So ux and ui we have already just now derived them. The uz is defined as the warping function which is unknown multiplied by theta. So the theta is brought here just to bring consistency between all the three displacements. So at this stage, what we have done, we have assumed two things. One is the angle of twist per unit length, which is unknown. And second, we have assumed what is the warping function, which is a psi. And in terms of these two unknowns, we have defined the ux, uy, and uz. So we got the displacement of the three values. So from this, one would like, in the next slide, we will see that from this one can derive the expression for the stresses. So what we have right now is ux, uy, and uz. And ultimately, we want to calculate what is sigma x, sigma y up to tau xz. So all the 6 stress components one would like to calculate from the values of ux, uy, uz. So that is called as a displacement approach for getting the stress analysis. Now you have already done some basic theory. So how to approach from displacement to stress, you already know in some blocks or in some segments in previous lectures we have seen. So can you tell what could be the sequence to reach the stress from the displacement? So given the displacement functions, so these are the displacement functions, how one can calculate the stress? It will be okay. Using strain. So what equations you will use from displacement to strain? Bar by ux by W x, or Cauchy's strain displacement strain equations. So using those equations, one can calculate the strain tensor or the 6 values of the strain values. One can calculate. So this is using the Cauchy's strain displacement equation. And once we have got the strain value, we want to calculate what are the stress values. So what is the relation between strain and stress? So how can convert a strain vector, a strain tensor to stress tensor? We are just now given T2, no? Yeah, Young's modulus is one component of that approach. Young's modulus, Poisson ratio, but what is the general approach called as? So you have 6 strain components, you have to convert to stress. The generalized Hooke's law is what we are going to use. So you have 6 by 6 matrix. Using that matrix, you can convert. So I think you have put that topic in option, most of you. Since yesterday only you have given exam. So using the generalized Hooke's law, one can calculate the stress values. So we are not going to cover this derivation, but this is the approach and one can see the details in the textbook. So we'll directly come to what is the solution that we are obtaining. So what we discussed in the last discussion, same is captured here. So first step we have already done. So we have calculated ux, uy and uz by using the approach that we discussed earlier. Then one can calculate from the displacement the strain values by using the Cauchy's strain displacement equations. One can use the generalized Hooke law to get the values of stresses. So these two steps are not shown here. So in the book you will find the derivation that is not in the scope for this particular course. But finally, what result you will get if you, from those displacement, if you write the stress values, you will find that all the normal stresses as well as tau xy, that is the in-plane shear stress, they are going to become zero, and you are only going to get tau yz and tau xz as given in terms of the warping function psi and the geometry and the angle of twist theta. So these are the values of theta. So we are not yet reached the final solution because we don't know what is the warping function psi. So without that we cannot do the further calculations. But this is the approach that one has found out. Now we also have studied the equations of equilibrium in the initial part of this particular course. So there are three equations of equilibrium. So gamma sigma x by gamma x plus gamma tau x y by gamma y plus x z by, and like this there are three equations of equilibrium are there. So whatever stress solution we have found, so in order to get the value of this warping function psi, we use the property that any stress solution must satisfy the equations of equilibrium. So we substitute these values into these three set of equations. Some equations will get automatically satisfied, but the other equation would give you a condition which the warping function must satisfy. So using the equations of equilibrium, if you substitute these stress functions into the three set of equations, one of the equations will give you the, and if you eliminate the theta, you will get the form or the property of this particular warping function. So this particular warping function, it satisfies. So this is called as a Laplace function. You might have studied in the mathematics, which comes in various equations of electrical engineering, mechanical and other domains. So we find that this particular warping function which we are trying to investigate, it obeys the Laplace function, and the set of equations, so there are family of functions which satisfy the Laplace equation, they are called as harmonic functions. So that is just a labeling, but what it means here is that the warping function, or if you twist a non-circular bar, whatever is that surface which gets generated, the nature of surface must be such that it satisfies the Laplace equation. Okay, so how to obtain this warping function from this Laplace equation is again another set of derivations which you get from the geometry. So the warping function is purely a function of cross section. So for circular cross section, it will be a very simple function. For elliptical, it will be another one, and so on. So given a cross section, using the solution of this particular differential equation, one can get the warping function. So that is what we understand here. So let's recap what we have done till here. So using the displacement approach, first we assume the displacement in terms of something called as a warping function at angle of twist. We converted those displacement to strains. We converted strains to stresses, and this particular set of stresses, they must satisfy the equilibrium equations, and that gives us a property of this warping function that they must satisfy the Laplace equation. And how to obtain this function is an entirely different topic. So again, that is not in the scope. So we are understanding how the theory of non-circular shafts is being investigated or being analyzed. Okay, so at this stage we know how to get the warping function, but our original task is to get the stresses. So that is tau yz and tau xz. The remaining stresses are proved to be zero through this approach. Now in this equation you have the warping function. How to obtain warping function is through the solution of this Laplace equation. So assuming that one knows how to solve this equation for a given shape, one will get the warping function. What additional thing you require is the theta, that is angle of twist per unit length, that is still remains unknown. So for that we will use another condition. So in the cross section, the cross section is subjected to external torque T, and at any point in this particular body, we are having these two stress states. So we are having tau xz and tau yz. So for the cross section, this is x-axis, this is y-axis, and the perpendicular is the z-axis. So this particular plane, or the plane of this screen, it represents the z plane. So on z plane, in the x direction is tau xz, and on z plane, in the y direction is tau yz. So these are the two stresses that we are getting. If this is the origin or the centroid of this particular cross section, we can take the moment of the horizontal force or the x direction force which is acting at this element and multiply it by the moment arm, and similarly for the x direction what is the vertical force and the moment arm, and add up all this together. They must get added. So this is internal moment. So summation of all internal moments which arise because of the shear stresses, that must be equal to what is the external torque. That is for the equilibrium of the body. So when you subject external torque, the inside material, it resists that moment and it generates these stresses. So these stresses are nothing but the internal forces. So these internal forces, they generate internal moment, and if you add all the moments, in short, instead of summation, it will be the area integral over this entire region, then you will get the torque value for this particular body. So that is how we calculate the angle of twist. The second unknown is calculated by using this particular set of equations. So again, we are not going into derivation of this equation. So directly the formula for T would be given as in the next slide. So we use this condition that torque is equal to the area integral of the all internal moments. So that takes the form as given here. So it is G multiplied by theta. So this is the form of equation what we get here. So this particular equation, the torque, which is the external torque which the non-circular body, non-circular shaft is subjected to. So T is known to us. G is the shear modulus that is known to us, material property. Theta is the unknown that we want to find out, and whatever you see inside is the geometric property. The psi is the property of the cross section, and x and y are the coordinates of the internal points of the cross section. So this integral also can be calculated either numerically or analytically, and hence one can calculate the value of theta by using this particular equation. Usually this equation is written in the form which conforms to the way the classical torsion equation is written. So our classical torsion equation is E by J equal to G theta by L. So this particular equation is, this particular equation is written in this particular form. So this implies that T equal to G J theta by L. So the classical equation, the torque is Gj multiplied by theta by L. In our nomenclature, this particular theta is angle of twist per unit length. So that is nothing but this particular quantity. So that theta is kept here as it is. G is kept as it is, and whatever is the remainder is written as G. So this particular integral is the value of J, so that this equation becomes, for use purpose, you can use it as a classical torsion equation and calculate the value of j by using whatever numerical or other methods, one can calculate j. Usually this value of the j for non-circular cross-section is available in design handbooks, or if it is a very complicated shape, then you will have to use numerical methods to evaluate this particular integral. So once we calculate the value of j from the geometry, one can calculate what is the angle of twist by using this particular equation. So that is the approach, and once one knows theta and one knows psi, then using the previous approach or the previous derivations, one can calculate the stresses in terms of theta and psi. So any design purpose or torsion design require two quantities: what are the stresses being generated and what is the angle of twist or what is the deformation. So the theta we got from the last analysis, and the stresses we get in terms of theta and psi by using this particular approach. So that is in summary, the most generalized or analytical way of handling non-circular cross sections. What we are looking here, in general, any cross section is given to you. You should be able to get the warping function psi for that cross section, and you should get the j integral or the j in the form of this integral for that cross section. So this is also geometric property, and the psi is also geometric property. If you can calculate these two values, then it becomes just like a regular classical torsion equation, and one can do the design using this particular approach. So that is the most generalized way. So here for this course, our understanding is just to understand the overall approach which can be used for any generalized case. In order to understand what is the nature of these warping functions, we will consider two geometries. One is the circular, which you are aware of, and the second is elliptical shape, so which is a non-circular geometry, and we will see how the warping function for these cases looks like. So you get a feel of how these bodies behave under the action of torsion. The circular cross section, for which you already learned in the previous semester, why it was you were able to derive those equations without doing all these complicated things, is because the warping function there is constant. So warping function, as you remember, it gives you the axial displacement of the shaft, axial displacement of the cross section. So its constant means whatever is the original cross section, every point will move by constant amount. So that is why the cross section remains flat, so there is no warping. And when psi is constant and you substitute in the previous equation, you will get the same equations as that given in the formula which you have learned in the third semester. Except here, instead of tau, which is given as ER by J, you get its x component and y component. So whatever is the shear stress component, whatever is the shear stress component tau, if you split into x component, y component, so these are the two components that you are getting here. So essentially it is the same formula as you learnt in the third semester for the torsion of the shaft. Point to be remembered is that for circular shaft, the warping function is constant. So that is why there is a constant displacement of the cross section. So cross section remains flat even after application of the top. Whereas the situation is not same for other cases. So as an example, let's see what happens in elliptical cross section. So in elliptical cross section, it can be shown that, again derivation not in our scope, that the warping function psi is as given by this particular formula. So it is A and B are the major and minor radius of the ellipse. So A is the major radius, B is the minor radius of the ellipse. So psi is defined in terms of the radii of the ellipse multiplied by xy. So it is some constant multiplied by xy. So that is the warping function for the elliptical cross section. And since psi represents the warping, that is how much out of plane the moment will be there, let's understand this particular function. So it is b square minus a square. So b is smaller than a. B is a smaller radius, a is a larger. So this particular quantity is a negative quantity. So some negative quantity multiplied by x bar is the psi function. So in the quadrant 1 and so in the first quadrant and in the third quadrant, so in this case x is going to be, both x and y are going to be positive. In the third quadrant, both x and y are going to be negative. So the product x into y will remain positive in this quadrant as well as this quadrant. So the psi function will be negative in these two quadrants. So that means in these two quadrants, the particles or the solid will go inside the board. So there will be warping. The warping will be such that in the first quadrant and in the third quadrant, the movement of this surface will be inside the board, and in the second and fourth quadrant it will be opposite. So x and y will be negative, so this product will be positive. So these points will protrude out of the board. So if you take an elliptical shaft and apply it to twisting, you will find that its diagonal quadrants, two quadrants will come out, they will protrude out, whereas the remaining two quadrants, they will sink in. So we will get shape which is sort of every 90 degree it will go in and come out. So it is like one quadrant it will come out, another quadrant it will go back, and it will happen in the both, in each quadrant it will be separate. So it will, the kind of shape that I shown here will happen in case of elliptical coordinate, and the values of the torque and the other components are the shear stresses for this component are given here. So this we will not be using, this is only given for information, we will not be using it for any calculation, but just to get a feel of what that theory, outcome of that theory that we are just now seeing is being shown here. And using this particular approach, one can do any kind of analysis for torsion. But in the next class, we will be considering a more specific case. So in that particular case, you don't require this complicated approach. So if you have non-circular cross section, but if it is a thin wall, so something like a tube or a pipe or a channel, rectangular channel, like this window frame, hollow cross sections. So if they are subjected to torsion, then to calculate the stresses, we don't require this complicated approach. One can bypass this approach and find in a simpler way. So that is what we will see in the next class. So any questions till here? So what you have seen here is, if there is a non-circular shaft, what treatment one would require in order to calculate the stresses and deformation. So the theta and the stresses in terms of warping function needs to be calculated. So let's stop here for today.